know we have taken long. Thank you for keeping following my YouTube, and I don't take it for granted. I promised every time I have anything that is better, I will do share with you guys, so that you also pick something, you have something, you also share. I also want to see some of the comments and new methods and approach that you are undertaking. Today, I just want to share a bit of experience on the response of an existing culvert to the loading environment and many other factors. We have a road project where we are doing upgrading, reconstruction, and upgrading it. This is the main northern corridor. So there were some few culverts that were recommended for demolition by the design consultant and also in-house team who made a validation of the design. But one of the subcontractors, I think, after demolishing one culvert, noted that the concrete grades or the residual strength was still high and wasn't suitable for breaking. When he reported to management, we were advised to go and inspect the remaining one to confirm whether we retain the culverts and just extend or demolish. So we did that inspection. So it was a single box culvert. This is the single cell box culvert of about 2.4 by 2.4 meters. It's in a low-lying area, Nopiola River, so you can see water stagnating in, and also you can see quite a lot of cobwebs. These are trees upstream and downstream, showing some kind of lapse in maintenance. Definitely, I always say we do design, we construct with the purpose of having it perform well for the design life. So design, construct, and maintain. Maintenance gets better if you do proper inspections and coming up with practical interventions. So we did this inspection. This is exactly this. We noted it's about 25 years old. We observed some cracks on the down here. We have some cracks up here. I'm going to show it in at a close stuff. Always we need to be kind of aware of keeping this structure free from this plant growth around the concrete area. Definitely it will create a different reaction mechanism which will affect the concrete grade and the durability. So when we did the inspection, we noted that actually the culvert lacked proper haunches or splay at the slab wall corner, bottom slab wall corner. What you're seeing here, this is just some structural plaster they applied sometime, and there's already scoring, not even the scoring, and also some honeycombing, which is observed, and so we realized that actually when this is the high water mark and this is the top. So this top slab, actually when you're breaking or demolishing, it looks so sound and good, but the lower part here, which is in contact full time, cyclic wetting and drying, is actually now not as strong as the upper one. And so when we did this inspection, we also note that there were cracks at the bottom slab and also external wall junction. So we tried to do a simple destructive to see whether this concrete was still, the residual strength was still good enough, because visually up looked good and you could actually see it, but down here, because of poor construction and also maybe poor construction, you're going to see at a close range, there's a lot of honeycombing, so that allowed ingress of water into the concrete body, interacting with reinforcement. And we also noted that the reinforcement had already begun corroding. We're also going to see that. So with the box culvert design has rigid frame. That's why I did this drawing. Someone may ask why. So when you look at the culvert here, when you're an inspector, that's why normally we say a bridge inspector need to also have knowledge of design, load path, the geometry. So when you look at a 2D, this culvert's about 2.4 by 2.4 box culvert. They have 2.3 meter walls and also slab, and then constructed in the early 2000s. This is on the northern road corridor. When you model this thing here, we've also noted the cushion on top. It's about 0.3 to 0.6. So when you look at the design normally for box culvert, when the cushion is less than 1, that means the axial load effect is directly impacting on the top slab and also on the side walls. So there's nothing like dispersion effect or dispersion factor or anything. It is direct axial load which affects these slabs. So this is the bottom slab. These are moments at the corner. So when you look at it carefully, these corners and these corners, if you don't handle them well and there's any defects initiating, definitely is going to accelerate the failure of that culvert, because the culverts are designed as rigid frames with corners taking on both moment, shear, axial. All the loads are taken there, so it is highly stressed. So that need to be kept. So that's why sometimes we do haunching. You're going to see a drawing down. That haunching acts in 2 ways. One, it helps to stiffen this joint, and also at the lower part also helps to with the score, because when you look at the water moving here, these corners are very sharp, and so if you don't try to reduce that sharpness, it gets scored very fast. So by use of haunch and an adequate cover, you should be able to, it takes time for it to do that. But when you're designing, you don't design with the haunch. Sometimes you design without, and the haunch can now only give you an additional benefit for functionality and response to loads. So these are the moments. And then also you have shear force. You can see shear force also concentrating at the bottom and at the corner. And then these are the axial. So we noted that actually from this drawing, if someone comes and the structure is already 25 years old, that means the bridge connection index or the culvert connection is reducing while the environmental loading and axial load are increasing. And so with the low grade of maybe say by 75% already reduced, that means about if it was started, that means you are about 25 MPa, and yet the axial load and the rest is going up. Definitely the rate of progress of collapse or progress of cracks will definitely be higher. And so that is now why at the design stage you need to sort of look at some of these attention during operation. So that is why a designer will always think aloud on how best the structure should be maintained to avoid that. So when we came here, we came down here. These are the cracks on top of the slab. So here, as much as it looks good, when you go closer here and you do inspection, cracks run in that direction. Cracks are running in that direction. Now, from this drawing, when a crack is running parallel to that, the word would be, if a crack is running perpendicular to that, definitely you will know these cracks are coming in as a result of the loading on or the load from the axle load, because of the bending, the nature of bending. But again, because slabs has a contour behavior of collapse, because of reinforcement pattern, it is a two-way, one-way. You find it's not like sharp, a point that it tends to move in a contour kind of line. So that's how the pothole can generate, and you see it moving circular, opening, widening. But what we noted, it appears maybe water ingress into concrete and started affecting the bond between reinforcement and concrete, and also water keeps going down, and then because of some of these challenges during construction, I think the density of concrete seemed to be getting less, and water got down, and then moving along the, if you look at this pattern, it's more along the reinforcement, and that means corrosion is already, you can even see the color, the corrosion has already triggered, it's already progressing, and there's a debonding. There's already a clear marked reinforcement is not fully bonded into so now water, it even caused a bit of crack already, and water now leaks here in the bottom. This is the soffit of the top slab. Now you can look at the same here, and then down here, of course up here you can see the orange is not there. There's a bit of quality control in the joints at this point. So those are some of the constructability issues that is always good to handle. Even the way this is done, that means up maybe they did not provide some kind of waterproofing. We did not manage to open that because it's a busy road. Now this is the bottom part. This is you can see the quality of concrete at the bottom. We were just using some small, even this stone, this boulder here is what we were using to knock this, and for this to get out. So you can actually see, and you realize that this thing here, this is the structural, this is structural plaster. It's no longer concrete. If you have a concrete class 30, this is now, you can see this was a poor construction issue. This is now not on a maintenance, though they needed to have applied maybe some epoxy grout along so that it would get in and then also do some protection to avoid ingress. So water managed to get in, and this is now the reinforcement. They're using the twisted bars. They are spaced at 200 millimeters vertically, then also that one. So now if I take you back, if you the inspector, you the bridge engineer, realize that a culvert has a problem at the base, what is your reference figure? You come here, you model this thing, you model it, you have moment, you have forces, you have, look at this shear forces at this point, and you have that, then you have that, you have bending and the rest of it. So if you have shear forces at the base, and even this axial load and then the bending moment, this one, if it is exaggerated, there's a value. You begin to realize that actually, if a culvert is designed for maybe about 75 to 100 years, let's say even if you talk of 50 years, at 25 you already have a problem. It means you are losing here two things. You're going to reconstruct, At the same time, at the design stage, you paid money to the consultant. At the construction stage, you paid almost this box culvert could actually be about if you look at Uganda currency, could be about 500, half a million, half a billion. That's it, 500 million Uganda shillings. Or yeah, between 300 to 500, including everything, rock fill and other things. So if that is the case, that is almost about 100 plus $1,000, maybe $150,000 almost. And all that you have now you are losing. It's not reaching the service life, because if it is well maintained, it will go. But this is now not only maintenance. This was constructability issue for this honeycomb to come, and this will definitely increase the cost of maintenance, because every time you do, you reduce the interval of attention. You maybe after every 4 or 5 years come back and again apply to control and avoid water ingress. So definitely this was basically that. And also the aspect of design, because the design was supposed to have a orange, a provision of an orange, even so quality control during construction, supervision. Even the carpenter and the concrete team did not do good work 25 years ago. So some of the things, it's very good that if we share these notes, those who are willing to pick few things should also know that emphasis should be put in supervision to ensure quality delivery. Structure, this infrastructure we do design, we normally presume that contractors do their best to really comply with the design requirements, so that it lessens the effort during operations, but sometimes become difficult and sometimes not very good. So this is actually your fear factor once. So as a designer, you get to know where is this located and how is it. So this has really gone, there's no more cement paste, nothing. This is now purely stone, and then the rusted element. So of course this thing could actually be retrofitted if it is required. It's just to arc all this, arc it in bit. Maybe you do maybe 3 meter, you arc it and you cast neo concrete up to half here, and with a proper then expose it and do neo concrete. Even come improve this area foundation, again do it, but also need to be remodeled hydraulically, and maybe another cell could be added, so that this can be retrofitting, could actually also work for this kind of challenges. That help in reducing waste of taxpayers' money. So the top step is already failed. Bottom part of the wall also failed, and so we noted that it was not possible to leave this structure here when the road is going to be upgraded for another 20-25 years, and with this failure rate of only 50% time, it's already failed to this extent. Definitely, if you leave it unattended to and you just do that, we don't know what happened. So it can actually have a exponential failure rate that can lead to disaster. So that is what we have. So this is the best practices. So here is what I would expect. This is not that typical drawing. This is a different one. This is a drawing I picked from another project we're handling. So if you look at these are the drafting guy puts play or orange, no problem. So 200 by 200, I would prefer at least 300, because when you have a cover, you're going to see a concrete cover, and then the aggressivity or the harsh condition of exposure. You may find that this water in contact has acidity level less than 6 pH, and therefore it will require a cover of 65-70 onwards. then even concrete grid would need to go up, so that you try to improve on the durability and avoid ingress and also carbonation into the contour reinforcement. So when you have slightly a thicker cover, that means this splay or the orange will slightly be improved, maybe to 300 by 300 or 250 by 250. Those are some of the things that need to be taken care of during design. So when you look at this and then you quickly come back here, you look at what we have here, and then you go and have this drawing. Definitely this was not done in line with good industry practices. So these are things, of course, done 25 years. This one is the design was done, I think, last year or early this year, and then maybe some improvements happening. Then down here, this is the reinforcement that you can have a look. So this is what I was saying, that if you have to have a reinforcement cover more than 50 or 60 or 75, definitely the orange here would slightly increase a bit, and that in a way would improve the orange, which will strengthen these joints and at the same time also reduce on the rate of scoring. So treatment at oranges or splays and rebar details on-site lack is critical. On-site where we did inspection lacked this detail, which is an important connection. Oranges plays two key roles of stiffening at the walls and slabs of box culvert and also score control. So this is best practice, and then you can compare with the inspected culvert. So these are some of the details you would expect, and then you do that, because if the orange also is less or the cover is less, definitely when the scoring happen in less than maybe 50 years, you again expose this reinforcement, which again will begin to corrode and affect the functionality of the. So normally concrete cover must reflect site conditions and then water and soil in contact. Yep, so this is a normal, this is now also we looked at what could have triggered that crack of the bottom slab, the top slab. Then we are saying the benefit of cushion on culvert, the help in distributing the axial load, dispersing it maybe at about maybe 30 to 45 degrees. So if you have a 150 kilonewton wheel load, definitely that by the time the pressure contact get on top of the top of slab, the pressure under the wheel will be actually a patch UDL, which is reduced, and that in a way will avoid that punching effect on culvert locally. So cushion plays a bigger role, but again you need to note that cushion less than 1 meter doesn't have impact. It does not spread. The top slab will definitely experience the axial load the way it is, but more than 1.5, definitely there's benefit. Two benefits are realized here. One, the stress distribution will be less, temperature effect will be reduced. Normally it is negligible and not included in the model, and even the tractive or braking forces also reduced or not even considered, because it will be now less. So both temperature and braking become minimal except for cushion of 1 meter and less depth. We observe that at the site where the existing field seems less than 600 mm, exposing top slab to high stress response from varying axial loads, including effects of temperature and braking. So the failure observed could be a combination of many things. You have contaminated surface water. You have weak concrete, which allow ingress of water into that and initiating corrosion. Then cracks developing, fatigue issues, temperature effects. So we need to be also mindful. If cushion is less, then more attention need to be done to protect the concrete from up. Then this is the best practice for trying to keep water away from the structure, or try to keep it at minimum to avoid causing a bit of problem. So this is water management, the stone pitching applied, for guiding water into the inlet and outlet. So what could you do differently? At design stage, you need to be mindful of maintenance. Always, these 3 stages are very important, that you honor these stages at your design stage. Look at the design it, conceptualize, design, construct, and maintain. Then come up with a very good inspection and maintenance manual to guide operations. But again, if construction is not done well, even maintenance become a challenge. There's going to be high cost of maintenance, because every time, like the honeycomb, every time you have to fill, after 4 or 5 years, go back, do. So if you do what they call assessment or whole life cost assessment, you may realize that in the next 50 years, the cost of maintenance could have exceeded if you were to build a new culvert. So basically, you need to pay more attention to detail at design stage. Then make sure construction is compliant. You monitor and ensure that whatever was designed is constructed. And then also at operation stage, it is important to make sure we do regular inspection to observe these critical areas that can trigger failures of critical sections of the structure. So these are some of the few observations that we did make at the inspection stage that are more of design coupled with construction challenges and even maintenance, because if you don't maintain it, because sometimes even if you construct an asset and it is not well done, definitely maintenance, you put a bit of money. You have regular attention. It is expensive, but it will not deteriorate at the rate at which some of these infrastructures are doing. Because if after every 25 years you want to upgrade a road, you also have to upgrade the structure. And yet these structures are designed for a duration of not less than 50 years. Then definitely there's a bit of misuse of taxpayers' money. And I think industry practitioners need to pay more attention in ensuring compliance and best practices on all public funded projects. Thank you.